Hey guys, if you have your proposals, remember I did push it back to Tuesday, but if you do have it, I'll take it today if you have it. Does anybody have theirs they want to turn in? No, I pushed it back because of the holiday, and I got several questions about it. So what I expect in the proposal, I've said this before, but what I expect is a paragraph, 4 or 5 sentences that just sort of describe the topic that you're going to do, how you're going to present it, and sort of the main ideas. So I just want to see that you've given it, a half hour of thought and just sort of see what you're expecting to do. And that might change a little bit, but all the main ideas should remain intact. All right? It is worth 20 points, so that's out of 200 points, so it's 10% or so. And if you do it satisfactorily, I expect that all of you will get 20 points. But if you just write, it's kinesiology, that's what I'm doing. Woo! We should get people to time it. Then you'll get less than that. Okay. Are there questions about it? No? People have asked me how long this is to be, the paper or whatever it is that you expect to do. I don't want to put a page limit on it, but I expect that that it's an adequate amount of time. How long did I say on the project? 5 hours, yeah, so about 5 hours. You know what it takes to make them 5 hours, right? Yeah, so just want to see something that's satisfactory and something that, remember, there is the opportunity for extra credit as well. And if you do an spectacular job, an excellent job, then you'll get more credit. All right? So especially if you didn't do well on this quiz, that would be a good place to pick up some extra credit. You had a good weekend? A good break? Was there any big news from the break? What did y'all do? Go to parades and stuff? You went to New Orleans? Yeah. See, I can hear everything. Like all y'all chatting over there, I can hear all that too. We went to Bogotita. Have you ever been to Bogotita? Yeah, we went up on the Bogotita State Park, which is on the river. Y'all been to the state park? You been down the river tubing or whatever, canoeing? Yeah. So we had a good time. It was rainy, but that was okay. We rented a cabin. All right. Let's make it start. Oh, I will return your quizzes after class today. Y'all did really great. The average was like 84%, so I think that's spectacular. It was an okay quiz, you thought? No big surprises? It was all right? All right. There were several perfect scores and I think about a dozen A's, so I appreciate your hard work on that. As I said, I'll return them at the end of class, and I'll put the solutions up for the quiz, kind of like the screencast and the homework, like a video solution of the quiz later today or tomorrow. The final that you'll take in this class, which is worth, I think it's worth 200 points. Am I right about that? Yeah, the final will be taken from the quizzes, so they'll be very similar to the quizzes. It will be cumulative. So hang on to those quizzes, and I'll post them online with the solutions because you'll use them later to study for the final. Is Kaylee here by chance? Kaylee? She's what? Okay. All right. Last time we started on Newton's laws. There were 3 of Newton's laws. Now, prior to Isaac Newton, the general thought, which was put forth by Aristotle, was that every object has what? What's that, David? No, that was Newton's law of gravitation. Like, that whole idea didn't really come about until Isaac Newton, that you had this attraction between objects of mass. But prior to Isaac Newton, Aristotle, for hundreds of years before Newton, Aristotle put forth this idea that that objects had a natural state. And what was that natural state? To be at rest, right. So objects were to be at rest. That's their natural state. And then Isaac Newton, in his first law, said, no, that's not true, that the natural state, that an object doesn't really have a natural state. It's whatever state that it's in. And so if an object's moving, it's going to continue moving until a force acts upon it. And if an object is stationary, it's going to remain stationary until a force acts upon it. What was that property of matter called? It's inertia, right. The first law is the law of inertia, and that property of matter that idea that it's going to stay stationary unless the force acts upon it, that's called inertia. All right? Mass is a measure of inertia, so objects with more mass are harder to move. The second law just described the relationship between the acceleration and the force. It was A was equal to F over m. So if you apply a force to an object, it's going to accelerate that object. We'll use that in some examples today. And then what was the third law? It dealt with what type of forces? Action, reaction. Yeah, equal and opposite forces. So anytime I have a force and I push on something, there's an equal and opposite force back. It doesn't have to be contact forces, though, right? When else can I have action, reaction forces? And this was sort of mind-blowing. I think it's mind-blowing. Maybe I think it's kind of cool. What type of forces also have these action, reaction forces? Right, field forces. Field forces, there are really just two field forces that we'll deal with. There are four total, but there are two that we'll deal with. Those are gravitational forces, like the force between me and the Earth, or the force between each of you with everybody else. Anything with mass feels a force between us, between those two bodies of mass, that there is an equal and opposite force between those two objects of mass. We watched a little video. Do you remember what is it that's thought to convey the force of gravity? Right, gravitons. And gravitons are these theoretical particles. We don't really know what they're like, but these theoretical particles that are thought to carry this force of gravity. And so we watched a little Superman video. They thought that maybe Superman can fly because he can in some way manipulate these gravitons. Right? There's an experiment, you remember, in Louisiana called LIGO, and they're trying to measure these gravitons. If they're detected, it's going to be the find of the century. Right? It's going to be big deal, like Nobel Prizes and all sorts of jazz like that. So if y'all can be a part of it, it'd be really exciting. All right, so let's work through some examples for Newton's law. And again, if you have your proposal, you can bring it to me at the end of class. But I will be picking them up in class on Tuesday. All right, now we're going to use Newton's second law. And Newton's second law said that the acceleration is equal to F over m. That says that if I apply a force to an object, it's going to provide an acceleration. It's going to cause that object to accelerate. We usually write this as the force is equal to the mass times the acceleration. But this is the way that Newton originally wrote it. And mathematically, it's the correct way to write it. But we'll just say that the force is equal to the mass times the acceleration. Now, when I look at the units of force, I can look at the expression. So if I were to determine what are the units of force, it's mass times acceleration. What would that be? The units of force. Well, mass is in units of what? Not grams, not in the MKS system. What is mass? Kilograms, right. So remember MKS, the K is for kilograms. Kilograms is the SI unit for mass. So I have kilograms, and then acceleration has what units? Was it, Joel? Huh? No, for acceleration. Remember, acceleration is the way that velocity changes with time. Right, meters per second what? Squared, right. So it's meters per second per second. For every second, how much does our meters per second change? All right, so if I were to look at the units, the SI units for this, I have kilograms here. For acceleration is meters per second squared. And so the units for force is a kilogram meter per second squared. But we're going to call this a Newton. So this is a Newton. And when you abbreviate it, it's the name of a person, so it's capitalized. So 1 Newton, which is the unit for force, who is it named after? The Newton? Fig Newtons? That's like my favorite cookie. It's not really a cookie, it's fruit and cake. No, it's named after Isaac Newton, right? So the unit for force is the Newton. Let's do a quick example. This is from your book. We haven't done this, have we? We haven't done any examples yet? No. All right. This is example 3.2 in your book, if you want to refer back to that. I'm going to write it out here. An orderly is pushing a gurney. And the mass of the orderly is 80 kilograms. I'm just going to write that out here. The mass of the orderly, this person, is 80 kilograms, so sort of typical size. The mass of the gurney is 20 kilograms. And it says the mass of the patient is 50 kilograms, so the smallest patient. 50 kilograms. And it says that the orderly pushes with a force of 150 newtons. And it asks, what is the acceleration of this gurney? If I have this gurney, this orderly pushing this patient on a gurney with this force, 150 newtons, what is the acceleration? Let's sketch out a little picture here. I have, this is my orderly. Here's my gurney. Here's the person on top of it. And then this guy is pushing this with a force in this direction equal to 150 newtons. And now I want to know, what is the acceleration? What happens as I increase the mass? What happens as I increase the mass of this? Will the acceleration go up or down? It's going to go down, right? It sort of goes back to our first law, this whole idea of inertia, that if I have a lot of inertia, it's more difficult to push something, to increase its acceleration, to change its velocity. So I need to consider the mass, but in this case, I have three components of the mass. I have the mass of the orderly, the mass of the gurney, and the mass of the patient. So I'd start here with Newton's second law, F is equal to ma. And then I'm going to solve this for the acceleration. The acceleration is equal to F over m. Now what I've done here, I won't always go through all the algebra. Let me just show you. I have F equals ma. I'm going to divide both sides by m. These cancel out, and then I have an expression for the acceleration. All right. Remember, if you have problems with algebra, you should come see me. I can really help you sort of work through some of those things. Our algebra isn't going to get real complicated, but we'll have some simple things to do. All right, so the acceleration is force over mass. So that's going to be 150 newtons. And what's my mass that I'll use here? Right, the sum. What is the sum of those masses? Andrea, what is the sum? 150. So 80 plus 20 plus 50 is 150. And so that's just going to be, that's in kilograms, 150 newtons over 150 kilograms, which is 1. And what are the units for the acceleration? Meters per second squared. Right. Now if I go back to my original SI units, I have a newton over a kilogram. And remember, newton is kilogram meter per second squared over kilograms. It leaves me with just meters per second squared. The units are fairly important when you're working through problems because it allows you to one, see if you've worked it out correctly, and just to make sure that your units are correct. So on the quizzes, you might see some questions where I just ask you, what are the units for force? And then the answer would either be a newton or it would be a kilogram meter per second squared. Like I might ask you, what are the basic units, the basic SI units for the newton? Is that clear what I mean by that? We'll see that as we go along because we'll start building units more and more as we go along on top of one another. So we'll add newtons with other things and create new and exciting units for you to know and understand. All right? This is a pretty simple example, right? We'll see some others where we have multiple forces. and we'll deal with net forces, where we're adding up vectors of different forces. Now, I want to go through, in your book, they have different sections on different types of forces. I'm going to go through most of those, and we'll work through some examples, and I'll show you some examples of some of them. The first sort of type of force is weight. These are types of forces. And the first one that they discuss is weight. This is the force of gravity on an object. All right, so going back to Newton's universal law of gravitation, where these forces between objects of mass, there's a force between me and the Earth, and we call that force weight. It's the force of gravity on an object. From Newton's second law, we say that the force is equal to the mass times the acceleration. And so our force due to weight is also going to be the mass times the acceleration. But we're going to call this acceleration g. And this g, this is the acceleration due to gravity. We've already used it a few times, but that acceleration is just 10 meters per second squared. All right, or 9.8 if you wish to use that, but on the quizzes and what have you, I'll just use 10 just to make the numbers easier to work with. So for example, if I have a 1 kilogram mass, so like the 1 kilogram mass that I brought in the first couple classes, y'all remember that? How many pounds do you think that was roughly? Y'all recall? What's that, Jocelyn? Yeah, it's a few pounds. It's between 2 and 3 pounds. And a 1 kilogram mass then has a weight of about 10 newtons. And to do that, I would just use Newton's second law. It's equal to the mass times the acceleration due to gravity. That's 1 kilogram times 10 meters per second squared, which is 10 newtons. What's a typical person weigh in newtons? I've given you this number before. What's a typical person weigh in newtons? Like me, for example. I'll think. I weigh 10 newtons, 500 newtons, 700 newtons, 1,000 newtons. Never recall. It's not 700 newtons. So a typical person is about 500 to 1,000 newtons. A newton is how much in pounds, you think, roughly? If a kilogram is 10 newtons, how much is 1 newton in pounds? What is it? Yeah, about 0.2. In fact, almost about a quarter pound. So, you know, I have an idea, which I might like, because a newton is a quarter pound. And so I've always wanted students to do this, but they never do this, is that you could go to McDonald's or something, and you could go up, and what's one of their most popular hamburgers? The quarter pounder. So instead of getting a quarter pounder, you could go up and say, hey, I want that. I want a hamburger. And just see what they say. I think it could be a lot of fun. Like you could do a little video, like a skit where you go up and your friends are videoing it, and you go up and you say, I want a Newton burger, and then you could get into this big long discussion at McDonald's about what is a Newton, and it's a quarter pound, and it's the same as a quarter pounder. All right, so the proposals aren't due till Tuesday. So if you want to do a skit like that where you would discuss newtons and the SI units and stuff like that, I think that'd be a great idea for a skit, a fun thing to do. All right? Or if you just want to do it on your own, just let me know what happens, like what you get in return. So a newton is about a quarter pound. Now, the acceleration due to gravity on other planets, can either be more or less. So for example, on Jupiter, do you think it's more or less? Is the acceleration due to gravity on Jupiter more or less than the Earth? Right, it's more because Jupiter has a much larger mass than the Earth. Or for example, on Pluto, which isn't really a planet, but on Pluto, what is it more or less? What is it, Joel? It's going to be less, yeah, so it's going to be quite a bit less because it has a much smaller mass. So the acceleration due to gravity on other planets can be different. So for example, on the moon, the acceleration due to gravity is about 1/6 of what it is here. And so that's G is 1.7 meters per second squared. You don't need to know that number. I'm just sort of giving it to you just for reference. So the weight then of an object, the mass remains the same, but the weight changes. And so, for example, our 1 kilogram mass is now going to have a weight of 1 kilogram times 1.7 meters per second squared, or 1.7 newtons. So when you move an object to a different planet, you know, the mass of an object is intrinsic, and that doesn't change, but the force that it feels due to whatever body of mass it's sitting next to can change. So y'all all seen the videos, right, of the men on the moon? Right, what do they do when they jump up in the air? They sort of float, right, because they're not accelerating as quickly, and that weight, the force due to their weight, is a lot less. They weigh about, 100 newtons instead of 700 newtons. I have a little clip. This is from the same documentary about Superman. And remember, I told y'all that Superman didn't always fly, right? What did he do? He would just leap tall buildings. And so he was just exceedingly strong that he could leap over these tall buildings. And the general thought of the day, back before Superman could fly, was that the reason that he was so super strong is that he was born on a planet that had a much bigger mass. And so if the planet has a much bigger mass, then how are you going to feel? Are you going to feel lighter or heavier? You're going to feel a lot heavier. Like if you were born on Jupiter, which would not be a very good place to be born, but if you were born on Jupiter, you would feel a lot heavier. And so growing up in that environment, your body would be strong. And then all of a sudden you move to Earth, like Superman was because, his planet blew up or whatever, then you would find yourself in a much lighter environment. So you could hop like the people on the moon. David? Like on Earth? No. No, I don't know. I've never heard of such a thing. He asked, can you create a heavier gravitational force, like increase the acceleration due to gravity on the planet Earth? No, you can't really change it because you'd have to affect the mass of the planet. Now, what they do is different. So when astronauts, they go up for weight, they simulate weightlessness. And what they do is they go up in planes, and then they let the planes free fall. Because being weightless is really just free falling. They go up in the planes, and then the planes will free fall, and then they're accelerating downward at 9.8 meters per second squared or 10 meters per second squared, and so it feels like they're weightless. All right, we'll get to that. I'm pretty sure we get to that later. All right, when we talk about net forces. Let's watch this real close about Superman. It's very interesting. I think it's interesting. All right, so let's move on to center of gravity. This is related, the center of gravity or the center of mass. It's related to your weight because the center of gravity is where you can imagine all of your mass or all of the mass of an object to be located. Let me write this down real quick. So the center of gravity, I'm just going to call it CG. Sometimes you hear this called the center of mass as well, but your book calls it center of gravity. It's the point on a body where the force of gravity is considered to act. Like I said, this is also called the center of mass, and the center of mass, which I'll abbreviate CM, you can imagine this is where all of the mass is located. All right, it's a point where you can imagine the mass of a body is located. All right, so different objects are going to have different centers of mass. For a person, where is the center of mass? Is it up here? Right, it's right here. Right? It's like right at your belly button, basically. And that means that if that all of the gravitational forces I'm imagining, I can imagine that they're all acting at my center of mass. We've already talked a little bit about center of mass. Or do y'all remember in the video about the high jump? How did the center of mass come up in that? How did center of mass come up? Remember, we had 3 different versions of high jump, which I'm about to demonstrate right here. No, I'm not. But in the version that people use now, I forget what it's called. Anybody know? I know I have several track athletes. Anybody know? You know? It's cane, right? Oh, do you know Jordan track? Huh? You don't do high jump. Okay, well, anyway. The most recent, the center of mass, like if this is the bar, the person comes running along here and he jumps over, but the center of mass of the person is always below the bar. Do you remember that in the video? And so, but in previous versions where you did this thing where you sort of jumped up high over the bar and then you landed on your feet, that's before the insertions, your center of mass came much higher up over the bar. All right, so the center of mass is just where we can consider our mass to be located for different objects. So like for a body, a person, it's right around your navel. Have some other things here. What about a meter stick? Where is the center of mass? I have a 1 meter stick. Where along this meter stick is the center of mass? At what centimeter marking? Right in the middle, right at 50 centimeters, because this is 100 centimeters. It's right at 50 centimeters. However, I can change it. I can take this is a piece of a lead sheet, and I can change the mass of this meter stick so that it's no longer in the center. I'm just going to take this lead sheet. I'm going to bend it. All right. Our center of mass was here. Where is it now? Is it still to the right, or has it not changed? To the right. So now my center of mass is somewhere over here. So if I take this off and I try to balance it, it should balance right at the center of mass. This is at 50 centimeters, roughly. All right. But if I move it, so I have this lead on here, now my center of mass is a lot shorter. Looks like it's about 75 centimeters or 70 centimeters. All right, so that's my center of mass. And I can imagine that all of the mass of this meter stick is located at this point. This is kind of a cool thing. This is just sort of what you can do. If you have an object like a meter stick, it really only works with a meter stick, and I'll pass it around. You can try it. If I have my fingers like this and I hold it level, I can bring my fingers together. And notice how sometimes one of my fingers moves and then the other finger moves. See that? It's always going to come together at the center of mass. Isn't that cool? Like no matter what I do, even if I do it more quickly, well, it might not work if I do it really fast. Let me see. Yeah, it always comes together at the center of mass. We might say, well, yeah, you're moving them 50 centimeters, right? You're moving both of your fingers 50 centimeters from the end. So that should make sense, right? But they're going to meet in the middle. But look, if I change the center of mass, and now my center of mass is more like 70 or 75 centimeters. See? Isn't that cool? Yeah, I can pass this around. You can try it. I think it's kind of fun. And I think your friends will like it too. Like if you go and you show it, you should always take a meter stick to a party. If you go to a party and show them, you can show them that and some lead sheet. But don't chew on the lead sheet, okay? It won't hurt you, but don't chew on it. All right, so just hold your fingers and then you can bring them together like this. I have another little thing. You might have seen one of these before. My kids love this thing. Here it is. This is just a little plastic bird, but there's something special about it. It has some masses, some very heavy masses in the wings. So where is the center of mass of this bird? Is it at the beak? Is it above or below the beak? It's below because there are these very heavy masses right in the tips of the wings. So it makes it very stable. And you can make things more stable by changing their center of mass. And so I can hold this bird on my finger and do all sorts of things with it. It hardly ever falls off. You can put it on your nose, on your head, and stuff like that. It's kind of fun. So you can find these in, I don't know, little science catalogs. You want to see this? I want this back, okay? So do not put it in your pocket. Nobody's getting out until I get it back. Let me try to put some of that in words. So for example, the center of mass of a meter stick. This is a 1 meter stick. The center of mass is going to be at 50 centimeters. This is the center of mass. However, if I take my 1 meter stick and I put a sheet of lead or whatever, I make one of the ends really heavy, now my center of mass is going to be closer to the end. For us, it was around 70 or 75 centimeters. All right, a person. This is me. A person's center of mass is right about here at their belly button. I need arms. Doesn't really look like me at all, does it? No. Now it does. All right, so that's your center of mass right about your belly button. There's the bird, and its center of mass is because of the wings. What about a garbage can? I have a garbage can. Where is the center of mass of a garbage can? This is kind of interesting. Not at the bottom. There's the center of mass. Is it inside the garbage can? Like, is it in the material of the garbage can? Because the garbage can is hollow, right? Where is the center of mass for a garbage can? Okay, yeah, it's going to be inside. It's going to be close to the bottom, right? It's a cylinder, and it'll be close to the bottom, but not quite at the bottom. It's going to be the point in the garbage can where you have basically equal masses on either side of that point. All right? You understand what I'm saying? Not at all, right? This is my, I should have brought a garbage can. This is my garbage can. My center of mass isn't in the plastic. Your garbage can is made out of plastic. It sits in space, but it's not actually in the material that the garbage can is made out of. So this is my garbage can, so my center of mass is going to be right about here, which is inside the garbage can, but not inside the material. Understand what I'm saying? It doesn't have to be inside the material. If it's a solid object, then yeah, but if it's a hollow object, not necessarily. I want to hold your fingers like this and then pull them together. All right. we've already talked about this a little bit, but this sort of falls in with gravitational forces. Newton's universal law of gravitation. You have a question? Yeah. Uh-huh. Right. Mm-hmm. Yeah. I'm not a gymnast, but gymnasts do this, right? Or yogis or whatever, right? They can sort of put their hands underneath them and balance themselves as if they're right underneath their center of mass. Any gymnasts here? Yeah, yeah, right. So you're a cheerleader, yeah. All right. Did I tell y'all my 08 joke? I didn't tell y'all this? Okay, I'm sorry. You always miss out on the jokes because it's Tuesday, Thursday class. What did the 0 say to the 8? And this is where y'all say, I don't know. What did the 0 say to the 8? Nice belt. Nice belt. You get it? 08. Yeah. All right, Newton's universal law of gravitation. So we've already talked about this a little bit, but it's just the idea that bodies of mass exert forces on one another. Two bodies with mass exert forces on one another. You know, Newton sort of came up with this based on planetary things, but later in the 20th century, early 20th century, this guy he built an experiment where he just took two metal balls, and he was able to measure the force between these two metal balls. It was pretty cool, actually, because they were just sort of normal mass things, but they were able to measure the forces between them. So if I have a mass 1 here and a mass 2 here, then both of these objects are going to exert a force on one another. And we see this on the planet. Right, here's North America, Europe, Africa. When we're standing on planet Earth, there is a force between us and the Earth. So the Earth is pulling down on me with how many newtons? A person is roughly what? About 700 newtons, right? And then likewise, I'm pulling back up on the Earth with a force of about 700 newtons. Similarly, there are forces between all of us that are not 0, but very difficult to measure. So very small forces because our masses are so small in comparison to the Earth. Newton said that this force, or he showed that this force is equal to G times M1, M2 over R squared, where this is the distance R. I'm pretty sure there are no homework problems in this. I won't expect you to use this. Is that true? There are no homework problems? You haven't done chapter 3, have you? I'm pretty sure there aren't. But I do expect you to know that if you increase the masses, that increases the forces. And if you increase the distance between the masses, what happens to the gravitational force? Does it increase or decrease? It decreases, right. So as I go further and further away from the Earth, then this gravitational force is going to decrease. If I increase this distance, then that causes the force to decrease. So this was sort of one of his big discoveries, this idea that there are masses between, or forces between objects of mass. He also, don't write this down, but I just want to show you something because, you know, we have this expression for the force. Don't write this down, but it's G M1 M2 over R squared. And then also this Newton's second law applied to our gravitational force, which says that the force is equal to mg. Now if we combine these two, because these are measuring the same thing, we can set them equal to one another. This is G m1 m2 over r squared. And then this is equal to m times g. This big G, by the way, this is just a constant. Newton determined it experimentally, but it's just a constant. It has a number. It doesn't really matter what it is. But here, I can solve this for the acceleration due to gravity, and it's going to look like this. The acceleration due to gravity will be G times the mass of the Earth over r squared. So there's this relationship between the acceleration due to gravity and the mass of the Earth. And that's kind of cool because that means that if you measure the acceleration due to gravity, that you're effectively measuring the mass of the Earth. There's this experiment called GRACE. And again, I don't expect you to know how to derive this equation. I just want to show it to you that there is a relationship. We've already talked about this. Between G, the acceleration due to gravity, and the mass of the Earth. There's this experiment. It's not flying anymore. I don't think it is. But it's a satellite that goes over the Earth. Here's the Earth. And then there's this satellite that flies over the Earth. Looks like a butterfly. But it's a satellite that goes over the Earth. And it has a pendulum inside of it that measures the acceleration due to gravity. And so as it travels around the Earth, it measures the acceleration due to gravity. Why would that be useful to measure the acceleration due to gravity as it travels around the Earth? What is the acceleration due to gravity? What is it related to? This is kind of cool, actually. It has very real applications. What is the acceleration due to gravity related to? What? It's written on the board. The mass of the Earth, right. So the acceleration due to gravity is related to the mass of the Earth, right? If you have a bigger mass of the Earth, then your acceleration due to gravity is bigger, right? If it's less, this is also true sort of locally. Like if there's less mass underneath me, then that means that the acceleration due to gravity is less. And this is measurable on the Earth. So where would you think the acceleration due to gravity would be bigger? In Louisiana or maybe on the Rocky Mountains? Right on the Rocky Mountains, because you have all this rock underneath you, very heavy underneath you, lots of rock and stuff. All right, so what this satellite does is it measures the acceleration due to gravity, and so basically it's weighing the Earth. So what applications does that have? To take the mass of the Earth. Why would you want to know the mass of the Earth? They've already seen it. Why would you want to know the mass of the Earth? What changes the mass of the Earth? It's not taking the whole mass of the Earth. It's just measuring the mass right underneath the satellite. So it can measure the mass over Colorado, or it can measure the mass over Louisiana. What would that allow you to do? Okay, no, not weather. I mean, weather is, compared to the mass of the Earth, is negligible, the mass of water in the atmosphere. Oh, that's a tricky question. What's underneath the surface of the Earth? What is there? Is there all right? Oh, you didn't? Okay. I thought you said the answer. Come on, what's underneath the surface? There are lots of things, right, under the surface of the Earth. There is the mantle, yeah, but what are some other things? Rock. There's rock. What? Minerals. Coal. Fuel. There's oil. And water. There's oil and water. So this mission, by measuring the acceleration due to gravity, can find water tables, it can find oil reserves and stuff like that. By measuring the mass of the Earth, it can find these anomalies like oil reserves and water tables and stuff like that. It's kind of cool, I think. All right. I have a little clip. This is an audio clip. Oh, I think I have it. Let me double check. That talks about a different way that they measure the mass of the Earth. Yeah, here we go. This is just an audio clip. I think it's from some talk show, and they're talking about how they measure the distance between the Earth and the Moon, and how this helps to measure the acceleration due to gravity. They're actually doing this out in West Texas. So if y'all ever go out to West Texas, there's a really great visitor center out at McDonald Observatory, and they at night they'll shine these lasers from this little stone building, this little brick building, up to the moon, and then they measure the amount of time that it takes for that laser to make it back because it reflects off of that mirror that's left on the moon. And from that, they can determine the distance between the Earth and the moon. And then by measuring that, they can calculate what is this gravitational constant that he talked about. He said that the gravitational constant is changing over time, that some people think that. And that's true, but it's not entirely true. They think that this gravitational constant might change over space. So like we look at things that are very small in the surface of the Earth in this sort of classical area of physics, but it's thought that maybe over very large distances, like over the distances of galaxies and over the distance of the universe, that maybe this acceleration due to gravity or this gravitational constant might change, or that there might be perturbations of such where you get these other effects. All right, let's look now at friction and the normal force. We know what friction is, right? It's if you have two objects that come together, friction will oppose the motion of those objects. So if I'm trying to push something across the floor, the frictional forces will oppose the motion. So for example, if I have this chair and I'm pushing it across the floor, what is the direction of the frictional force? I'm pushing it what? To the right? What's the direction of the frictional force? All right, it's going to be to the left. Almost always the frictional forces will oppose the direction of the motion. So frictional forces arises when you have contact between two surfaces. It's a result and it almost always, we're just going to say it always opposes the direction of motion. There's some very special cases where it doesn't, but it always opposes the direction of motion. The friction is proportional to the normal force. Let me show you what normal force is first. I'll do it over here on the right. The normal force if I have an object, let's say I have a guy sitting in a chair. All right, he has a certain weight, right? He's pushing down on this chair with his weight. The normal force is going to be that force that opposes that. So the chair will push back with an equal but opposite force. So this is my normal force. It's a result of that, of which of Newton's laws? The first, second, or third? It's this equal and opposite reaction force to the weight of the guy sitting on the chair. So which is that, 1, 2, or 3? It's the third law, the action-reaction. So this normal force arises or is explained by Newton's third law. I can have other normal forces. Like for example, if I push on this, then the surface of the table is going to push back with a force that's equal and opposite of the force that I'm pushing on the table with. That's a normal force. If I just stand here, I have 700 newtons pushing down, and then the floor is pushing back up with how much? 700 newtons. All right. So this normal force is just this action-reaction pair of forces. Now, the friction is proportional to the normal force. That means that if I increase the normal force, I'm going to increase the friction. So for example, if I have this chair and I push it across the floor, there's a frictional force that's opposing the direction of the force, right, that I'm pushing on. What happens if a person sits in the chair? Is it going to be more difficult, easier, or the same to push that chair? More difficult. So I can envision then that that frictional force has increased, decreased, or stayed the same. It's increased. The frictional force is increased. And that's because my normal force is increased. So when I have a person that's sitting in the chair, then it increases the weight of the chair, which increases the normal force. So my frictional force is proportional to the normal force. Frictional force is proportional to the normal force. And mathematically, we can show this, that the frictional force, this will be my frictional force. I'll use a lowercase f, script f, will equal to some constant times the normal force. I'm going to call this mu. This is the coefficient of friction. There's a table of your book that has coefficients of friction in it. You'll need it for a couple of the homework problems, the coefficient of friction. This coefficient of friction just describes the frictional forces for different surfaces, because if you have different surfaces, you're going to have different amounts of friction. So for example, if I have metal on ice, all right, that has a certain amount of friction. What if I have wood on rubber? Would that be more or less friction than metal on ice? It's going to be more, because that coefficient of friction between wood and rubber is going to be bigger than it is for metal and ice. That table is in your book. Let me look up the page real quick. It has those coefficients in Chapter 3. Did you need it for a few of the homework problems? Oh, it's on page 39. This is on page 39 in your book. All right. There are two types of friction. There's kinetic friction, and then there's static friction. And then there's static friction. Kinetic friction occurs when the objects are moving. And static friction occurs when the objects are stationary. All right, can you give me some examples of kinetic friction? What are some examples of kinetic friction? That is friction between two surfaces when the objects are moving. Some examples. Not the tires on the road, actually. Tires on the road, that's, most people usually say that. The tires on the road as they're turning, that's an example of kinetic friction. But if you think about it, that's between the surface of the tire and the road, and this is a good test question, by the way. What is the type of friction between a rolling tire and the road? And we'll talk more about this in a bit. Between the tire and the road, that tire never moves with relation to the road. It rolls, but the surface of the tire doesn't move with relation to the road, except in special cases. And when is that? Right. If it's on ice, or if you do what? If you do what? Right, if you hydroplane, or if you slide, right? So if your brakes lock up, and we'll talk about this in a minute, but if your brakes lock up, then that means that your tire stops rolling, and then your tire skids across the road. Now that is kinetic friction. So when your tires lock up, when they stop rolling, then that's kinetic friction. Give me another example of kinetic friction. Like curling. Yeah, curling is a good example of kinetic friction, where they have the thing like, what is it, a puck or something? A piece of granite. Is it a big stone? Yeah, and they're trying to get it to go down this ice to make it smooth as possible to make it go, right? What else? Kinetic friction. Ice skating, right? That's kinetic. You have two surfaces that are moving with relation to one another. Anytime you have two surfaces that are moving with relation to one another, you have kinetic friction. In your joints, you have kinetic friction, right? As they move with relation to one another, rubbing on one another, that's kinetic friction. What about static friction? We've already said one. Tires rolling on a road, that's static friction. What else? This is a little more difficult to come up with. Let's say that I'm trying to push a box or a crate or whatever across the floor, a piece of furniture, but I'm not able to move it. Then what is the friction that's at work there? Static or kinetic? Static, right? So whenever the surfaces aren't moving, the objects are not moving, that's static. And a curious thing about this, and a lot of sort of cool stuff comes about of it, is that static friction is almost always bigger than kinetic friction. Is bigger than kinetic friction. You can see this most obviously when if you're trying to push a big piece of heavy furniture across the floor. What happens after you get the furniture moving? What happens? Is it easier, more difficult, or the same difficulty to move that furniture across the room? It gets easier, right? And you can feel this perceptible shift that it takes an initial big force to get it moving, but then after you get it moving, it's a lot easier. It almost slides across the floor like metal on ice, right? That's because that static frictional force is almost always bigger, and so when the objects are stationary, that force is bigger, and you have to overcome that force, and once you overcome it, then it's easier to push that object because the static frictional force is bigger. Another thing, and y'all can try this when you leave here today, is when you're driving in your car, and you might not have ever witnessed this, but probably not, but you can try it today, because you have to come to a complete stop at a stop sign. Do y'all usually do that? Oh, try it. Yeah, thanks, Clara. When you come to a stop sign, try pressing on your brakes very slowly and just come to a rolling stop very, very slowly. Well, what happens just before you come to a stop? You might know? Yeah, you have a little shift. And that's because you're going from what type of friction to what type? You're going from what to what? You're going from kinetic friction because your brake pads are engaging with the rotor inside your wheels, and they're slowing down the wheel. And then just before it stops moving, it goes to static friction. And your car will sort of lurch just a little bit. So after you leave here today and you get in your car when you're headed out campus, when you come to that stop sign, just come to a very slow stop. And then if you have a friend with you, you can explain to them, well, did you know that static friction is almost always bigger than kinetic friction? It basically is always bigger than kinetic friction. Yeah, just drive, for goodness sake. Sick of hearing about all this garbage. All right, so y'all try that out, and there's this little lurch, and that's because you're transitioning from kinetic friction to static friction. That's pretty cool, huh? I think it's kind of neat. Y'all try it out when you leave here today. All right, so let me write that in words. So this is exhibited, for example, when you're moving furniture. It's easier to push when moving. And when your car is coming to a stop. There's a lurch. It just sort of lurches forward a little bit. All right. I want to show you a video where you can have two surfaces that have a particular coefficient of friction, but then you can alter the surfaces which will change the coefficient of friction. What can you do to the surfaces that will alter the coefficient of friction? If two surfaces, say rubber and asphalt, what can I do to those surfaces to change the coefficient of friction, to decrease the coefficient? What's that? I can smooth one of them, just physically make them smoother. I can also do what? I can put water on it. Like when the roads are wet, they're not as sticky, right? You have less friction. Or if they have oil on them, or if they have ice on them, even worse. Right? So this is a video. It's from the Olympics from the summer. It's the women's triathlon, and they had a very unfortunate thing happen where on one of the turns they had oil on the roadway, and it just led to a lot of crashes. But it's kind of cool. Like, I really like the triathlon. It's pretty neat. So let's just watch this.